Hey, welcome to Rational versus Irrational Numbers, my fellow number nerds. We're going to get started here by looking at a few terms just to make sure we are all on the same page. The first term here is we are looking to figure out what we call the set of numbers that are used to count objects. And yes, my friends, it is truly that easy. We call these the counting. Got a crazy action going here. We'll see if I can get it all figured out. We call these the counting or natural numbers. So either one of those terms would be acceptable. And those are simply the numbers you learned from the time you were little. You started counting everything, 1, 2, 3, so on. The next level up of numbers that we have are what we call the whole numbers. Now, the whole numbers aren't drastically different than the counting or natural numbers. They are just all of the counting numbers plus 0. As a 7th grader, you learned about the next set of numbers. Those we call the integers. Integers are the whole numbers and their opposites. 0 is an integer, but it is neither positive or negative. So far, these numbers have been building out. We start with counting or natural numbers. Then we've got whole numbers, which are all of the last set plus 0. Then you've got integers, which are all of the whole numbers plus their opposites. And finally, as a part of this group, we have what we call the rational numbers. And those are numbers that can be expressed as one integer, and we usually say one integer a, that's why that a is there, divided by another integer b, as long as b is not 0, because we know we cannot divide a number by 0. That is an operation that does not work. If I say to you, I have 4 cookies and I want to divide them among 0 people, there is no way to do that. So we are not allowed in math to divide by 0. Now this takes care of one kind of grouping of numbers. There is another aspect to this, and we call the other aspect irrational numbers. They are the set of all numbers that cannot be expressed as a terminating or repeating decimal. So we've got these two main groups. We've got rational numbers and we've got irrational numbers. Within the set of rational numbers, we've got counting or natural numbers, we've got whole numbers, we've got integers. And then we've got this set of irrational numbers. Now, those are the numbers we've been studying quite frequently and looking for Pythagoras. Most square roots are irrational numbers because we have no pattern to the digits, and those digits just go on and on and on forever. The most famous irrational number is pi. However, interestingly enough, when we lump these two groups together, the set of the set of rational and irrational numbers together is called real numbers. Now, for some of us, we like to see that in a little bit more of a visual fashion. And you know the amazing artist that I am, but we've got here in the center, those are the counting or the natural numbers. You can go ahead and on your notes, go ahead and write the word out all the way. I don't think I'm going to have quite enough room, especially in that small circle. Then, moving its way out, we have the whole numbers. Now remember, whole numbers are all of the counting numbers, and the only extra thing we add in is that number 0. So you see, as you move out, the whole numbers are everything in that piece of the circle plus all the parts in the middle. Okay, then the next piece of the bullseye are the integers. And those are all of the whole numbers and their opposites. So again, you got to keep it with numbers, whole numbers, the numbers we could count. So we're not talking about decimals here. Now, integers can be written as a fraction. So I could say 4/2, which is really 2. So as long as it can be simplified to a whole number, it constitutes an integer. All right, then the bigger group were our rational numbers. Now, as you continue to move on through math, you will be asked at times to distinguish between these groups. So, if something is a rational number, that means it's also an integer, a whole number, or a counting and natural number. So we can work our way back down, but we can't work our way out. If something, I said that backwards. Let's try that again. If something is, I'm sorry about that, guys. If something is a counting or a natural number, it can work its way back out. So a counting or a natural number is also a whole number, an integer, or a rational number. If something is a whole number, it may not be a counting or a natural number, for example, if that whole number was 0, but it will be an integer and a rational number. If something is an integer, it may not be a whole number, and it may not be a counting or a natural number, but it is a rational number. So, you can see we can work our way out, not back in. Sorry about that little mistake there. All right, and then over here, you have every, in this next category, you have the irrational numbers. Now, together, all of those make up the set of real numbers. So over here in irrational numbers, we have those non-perfect squares. So, for example, the square root of 2. However, the square root of 4 would actually fall even into that whole number category because it's a 2. So it would fit in as a whole number, an integer, and a rational number. Now, we were talking about decimals, and we stated, or I stated earlier, that irrational numbers are the set of all numbers that can't be expressed as a terminating or a repeating decimal. A terminating decimal has an end. It ends after a limited number of digits. So, for example, 1/2 is the same. All right, now it's going to give me grief here. Sorry about this. Is the same as this decimal. 3/4. All right, is this. 1/8 is this. So you can see that terminating decimals, or what I want you to see here is terminating decimals have an end. The other type of decimal that we have are what we call repeating decimals. Repeating decimals have repeating patterns of digits. For example, some of the more common ones that we are familiar with is 2/3, which is a 0.6 repeating, 1/3, which is a 0.3 repeating. Now, some of those repeating decimals have some interesting patterns, and that's what we're going to explore next. Right, you will see here that I have a chart that I have established. And in this chart, in the left-hand column, we have fractions with 9 in the denominator. And in the right side of this, these 4 columns here on the right side, we have fractions that have 11 in the denominator. What I'd like you to do right now is pause, grab your calculator, and go ahead and pause this and fill in this chart. Go. All right, hopefully that took you a little less time than it took me. My pen and this OneNote program decided they weren't going to cooperate and work together. But hopefully you started to see a pattern. When 9 is in the denominator, it was simply the numerator repeating itself over and over and over again. Now you will notice, I don't know if you can see it real well. Again, here's where I kind of was struggling with my pen and the OneNote program, but I have a decimal and then 111, and then I've got 3 dots after that. We call those an ellipses, and they simply mean that this could continue on and on in this pattern. Okay, same thing. So hopefully that was the pattern you were starting to notice with the 9s. Now, again, we've got another pattern with 11 in the denominator. This pattern, you will notice, or hopefully some of you noticed, that the numerator times 9 is what you ended up with. So we had a 0,9 repeating, a 1,8 repeating, and if I was going to write this and be real technical about it, I would write it this way, and I would put the repeating bar over the parts that repeat over and over and over again. So you can see that each time this, when 11 is in the denominator, we start off with a 0,9 repeating, then we have a 1,8 repeating, a 2,7 repeating, a 3,6 repeating, and you can see that each time it's going up by a 0.09. So that's why I said you could just multiply your numerator times 9, and that is the 2-digit piece that repeats. Now, an interesting item to note that when only 9s are in the denominator, the numerator will repeat. And what I mean by that, so the numerator repeats. And what that means is if I had 99 in my denominator, the 2 digits in the numerator would repeat. So if it was a, let's say it was a 4, the piece that would repeat would be 4 written with 2 digits. If it was a 15 in the numerator, it would be a 1,5 repeating. Okay? Same thing would work if we had 999, but with 999, 3 digits would repeat. So if I had 999 and I said 72 over 999, that would be simply a 072 repeating. Now, hopefully you can see that that pattern will continue forever. Whatever number of 9s are in your denominator, that's the number of pieces that has to repeat in your numerator. You can also see that same sort of pattern with 1s in the denominator. So if I had 111, take a minute and explore that and kind of see if you can get a feel for what's happening. Plug a few things in, try them out with your calculator. Now on this last section, I would like you to give these 7 problems a try. Please make note in the first 5 when you